Now question 4. Which of the following quantities is required to measure for the calculation of viscosity? Remember Stokes' law, F is equals to 6 pi eta r times velocity. R is the radius, V is the velocity, which is the terminal velocity actually. So we need the viscosity. Viscosity means this eta. So eta, for eta we just need this R and the terminal velocity. So do we need the density of the liquid, the mass of the liquid, the temperature of the liquid, or temperature of the room? Okay, they've given us different situations, different scenarios. From the density of the liquid, we can get density is mass upon volume. Okay, and this could give us the volume and the mass of that particular liquid. But for calculation, for the velocities, upthrust, for the upthrust, you need the density. For the upthrust force, you need the density, rho Vg. You need the density and the volume as well. But you also know that the greater the density, the greater the viscosity, right? So this can be a better answer. Whereas about the mass of the liquid, I don't think you need any mass. The temperature of the liquid or the temperature of the room, well, the temperature of the liquid is required because as you change the temperature, the viscosity has to change. So, but the density is also required. Now this is a best choice question. It's the temperature that is required. Let's see what the marking scheme has to say about this question. It's A, it's a density. And what's the reason? D is not correct because temperature is not required. And these things are not required, it's only A. Yeah, I'll research this one out and send you the answer. Now this one, which of the following should the student not do? Keep the temperature of the liquid constant. Yeah, the temperature should stay constant, otherwise the viscosity will change. Drop the sphere close to the side of the cylinder. Is this advisable? No, that's not advisable because of course that would, the cylinder's wall would apply a resistive force on it and allow it to reach the terminal velocity that's required, and check for zero error, that's also required, so it's B. Yeah. Move on to the next. Okay, so we are done with the MCQs. Now coming to the theory. Student determine the acceleration of free fall by dropping a cricket ball from an upstairs window. The student timed the fall just using a stopwatch. Explain why dropping the ball from an upstairs window rather than from one closer to the ground improve the accuracy of the experiment. Any idea? Why? Upstairs window means greater height.
Okay, right.
Greater height means greater time, and greater time can easily be measured. This reduces the percentage error because the greater the value, the lesser the error. Okay, so we can, okay, this is for 2 marks. So we can have a few points in here with the experimental point of view, of course. So upstairs window has a greater height above the ground. Upstairs window has greater height above the ground. So easier to measure the time. Secondly, the student determine the acceleration of free fall. How will he determine the acceleration of free fall? Using the formula S is equals to ut plus half at squared, where u is 0, half at squared is there. Now the value for acceleration from here will turn out to be 2s upon t squared. Now the greater the time taken and the greater the distance taken, the lesser would be the percentage error. Okay, do you know the formula for percentage error? It's error upon the measured value multiplied by 100 upon the value times the 100. Okay, so if the value of acceleration is large or the value of the displacement and the time are large, If this value is large, then the percentage error has to reduce. Okay, because the value is in the denominator, right? It's easier to measure. It reduces the well, the human reaction time error is constant, because when you're using a stopwatch, there is always a constant human error over there, human reaction time
Right.
error. But in addition to that, you'll have bigger manageable numbers of time. So this would actually improve the accuracy. You'll have bigger value for time, bigger value for time, which again has a more accurate result. So let's look at the answer. 6. Greater time reduces percentage error. Okay, those are the 2 points that they wanted. We wrote them. Clear?
Yeah.
Okay, now a second student stood outside and recorded the motion of the ball using the video camera on a smartphone. Explain why this method would produce even more accurate result for the time than using a stopwatch. What did I tell you? What error is associated with the stopwatch? Human reaction time error. Human reaction time error is present with stopwatch. So will give inaccurate time reading or will give a longer time reading. Secondly, the video camera can be paused, right? The video can be paused and can be replayed, can be replayed frame by frame to accurately measure the time, accurately measure the height, actually. Accurately measure the time and the height. Well, actually not the height, accurately measure the time. The time, it's actually the time, okay? Accurately measure the time. So it can be replayed, it can be stopped, it can be watched again and again. Start and end points more clearly, reduces the problem of reaction error. Recording can be replayed, so data can be checked. Recording can be analyzed, so a graph of motion can be plotted. We actually got the marks. These are the valid points that do match the marking scheme, okay? Get it?
Yeah.
Okay, these are in accordance to the marking scheme, but it's better to go with the wording of the marking scheme as well, if you want. Now, question 7, a student is asked to determine the Young's modulus of a metal wire. Okay, we did this experiment as well. If you've watched the video of Young modulus, there was an experiment of calculation of measuring the Young modulus, and we did that in theory, something like this. Please do watch this video. It has a detailed experiment of determining the Young modulus. There's a scale placed over here, and there are some weights. Some weight is placed inside over there, and then this tension causes the spring to extend by a certain extension. This gives us extension, and the formula for Young modulus is FL over AE. So the E,
Okay. Yeah.
the E or the X is over here measured by this ruler, and then this F is actually the weight which is applied, and this L is the original length, and the force is this weight. The cross-sectional area can be measured by first measuring the diameter using a micrometer screw gauge or a vernier caliper, and then using that and the formula for area pi d squared upon 4, we can get the area, the value for area, and this will give us the Young's modulus. Okay, so they also want us to draw a label diagram for the experiment. Uh, Standard laboratory operators are available, and a graphical method needs to be used. Okay, so they want us to use a graphical method. Okay, so it's easy. Basically, now you need to use the same formula and determine what graph should you make whose gradient should correspond to the Young's modulus. So using the same equation, I'm going to rearrange the equation. E is equals to FL over AE, right? AE. Now I need to change this such that I get two values or two quantities whose different values I can take. Okay, first of all, identify two quantities whose values you can vary. Can we vary the weight? Can we vary the force? We can change the force. Can we change the force?
Yeah.
Like if I replace this with a heavier object, the force will increase, right?
Yeah, yeah.
Okay, we can replace the force. And can we replace the length of the wire, this original length of the wire? If I place this, meaning instead of keeping this block over here, if I pull it backwards and the wire length of the wire increases, right? I can
Yeah.
even increase or decrease the length of the wire. So I can make a graph of length against the force, length and force graph. Now let's see the relationship between length and force. It's actually an inverse relationship. But now let's see what can we do over here. Make length and force. Let's draw out an equation. So it's going to be E A. Okay, instead of the length, we can also measure, we can also change the extension, right? Force and extension graph can also be made. Force against extension graph, in fact, is going to be a better option than using a force length graph, because
But
this is
how do
the
we
one
figure
which,
out what graph to make?
okay, so for the graph, you need an independent variable which you can vary, in this case, the force, and another variable that is dependent, that depends upon that value, meaning another
Okay.
variable that will, whose value will change if you change the value of f.
Okay.
So the
Right. Right.
extension, according to Hooke's law, it will change if the force is changed, right? Because
Okay.
they
Yeah.
are actually proportional. So we can actually, if we rearrange this formula, it's going to become f is equal to, you take both the a and the small e to the other side. So it's going to become e a multiplied by the small e divided by the length. Okay, I brought this length down here. So if you look at this, this is actually Hooke's law. Why am I saying that? Because young modulus is constant, right?
Yeah.
Area is constant, right? Area, the cross-sectional area of the wire,
Yeah.
and length of the wire is also constant. We are not changing the length. If all of these three are constant, then we can say that the force is proportional to extension, right? Hooke's law.
Yeah.
And if we replace this proportionality sign, we could have placed a constant and equal to, right? This constant is actually equal to EA upon L. We discovered this in theory as well. So now, once we draw the graph of force against extension, we are going to calculate its gradient. The gradient will equal the EA upon L, and then we are going to multiply the gradient by the length and divide it by the area to get the Young modulus value. And once we get the Young modulus, that's the answer. But again, we have to repeat the experiment with different values of forces and extensions to get the Young modulus answer, so as to get a straight line passing through the origin. Now, let's see the step-by-step procedure which they want us to follow over here. Okay, it's a long question. So it's long question, but it's easy. It's similar to paper 5 of P2 and paper 3 of P1. Paper 5 of A2 and paper 3 of AS, the Cambridge one. So
Right.
let's see. So this was the basic knowledge that you needed to have for solving this question. First of all, a student is asked to determine this Young modulus of a metal in the form of a wire using graphical method, and standard laboratory apparatuses available. We need to first draw a graph and then list the additional apparatus which is required and not shown on the diagram. And then we need to state the quantities to be measured. Then we need to state what is the independent and the dependent variable. And then we'll need to state for one of the quantities listed in C, explain the choice of measuring instrument. And then we'll need to comment on whether repeat the readings are appropriate or not. And then we'll need to see explaining how the data collected will be used, including a sketch of the expected graph. And then you'll need to explain the main source of uncertainty of the systemic error. And then we'll need to comment on the safety. Okay, commenting on the safety. Right, so now let's first draw out the graph. Okay, so use the lined paper. Okay, do not use this paper if you want to draw out the graph. Sorry, not the graph, the diagram. So for the diagram, this is a table that we have, and at the end of that table, we have a pulley. Okay, this is our pulley.
Yeah.
And over the pulley,
The wire.
the wire, correct, which is fixed at one end over here to a hook.
Clamped by two. Okay, by a hook or clamped by two boxes.
Yeah, you can do that as well. Caught by two boxes, yes. But that's gonna be a bit difficult to handle over here. Oh, or you can do that. Yeah, you can do that. Definitely you can do that. Like you are saying in between two boxes, right?
Yeah.
Yeah, you can do that. And the wire goes down. And over here we have a pan. And in this pan we can place in the weights. Label it as mg, the weight itself. This is gonna be the tension in the wire. And then you'll have, this is, okay, this is our ground. Although we don't need the ground over here. Now we also need a ruler over here. Why a ruler? Why a ruler?
To measure the extension.
Yes. And also to measure the original length of the wire.
Then
And on this wire, we are gonna place a spot or a pointer
marker.
or a marker that would be pointing towards the 0 mark on the ruler. Okay. So
Okay.
that when we add the masses over here, this pointer will move forward, giving us a value for the extension. Get it?
Yeah.
Okay. Now, once you have this experiment made, this is all you need, okay? Nothing else. Then the second step is list any additional apparatus required that is not shown. Okay, any additional apparatus that we need. Do we need any additional? Okay, label it as well.
We can add
The
cushion
pan.
at the ground in
Why?
case it falls.
Okay, that's a safety measure. Correct.
Yeah.
Cushion should be added, but you don't need to draw it, okay? You just need to list it. But cushion is in the end, it's just safety. Okay, this is the weight. Or you label the mg, that's fine. This is the tension in the wire. This is your pulley. This is your ruler or the meter rule. This is a pointer. And that's it. In addition to this, what's the formula for the Young modulus? Is E is equals to AE upon, sorry, FL over AE, right? We don't have the cross-sectional area, right? So additional apparatus is gonna be the vernier caliper. Additional apparatus required, vernier caliper for measuring the diameter, okay? Not the area. Why not the area? Can't we measure the area with the vernier caliper?
Yeah.
We cannot, okay?
Why not?
Vernier caliper measures the diameter, not the area directly. Area has to be
So
calculated using the formula.
for the diameter, we can like calculate the area, right?
Right, yeah, right. We can calculate the area, not measure the area. Calculate and measure are
Oh,
two different things. Okay. Then area
yes,
can be
yes.
calculated using the formula pi d squared upon 4. You have to write down the statement, okay, that area can be calculated using this formula. Then what's the second thing? Okay, this additional apparatus is just a vernier caliper. Then the quantities to be measured. Okay. It's better if you write down C, quantities to be measured, or you can write down a continuous answer. It's up to you. Quantities to
I
be
think it's
measured.
better if we alphabetically write it.
If you,
Like write it with the letter.
okay, you can do that, but I think the marking scheme has allowed writing it without. Okay, they did write it with the letter, so yeah, we are gonna do that. Quantities to be measured. Okay, so quantities to be measured include, what are the quantities? Come on, list them. The original
The
length.
length of the wire.
Original length, okay, original
Original length.
length. Oh yes, we missed out one other additional apparatus. Do you see? What other additional apparatus should we need? There's one more in this experiment. How are you gonna measure the weight?
Right, pan balance.
Yeah, the mass balance or the pan balance. Okay, so you could add that. And mass balance for the weight. Or the mass actually, not the weight, mass. Mass balance for the mass. Or the weight as well. Yeah, mass balance does measure out the weight as well directly. Then quantities to be measured are the original wire of the length, then the weight of the load that you put into that pan, that hanging pan, and then what else? Diameter of the wire,
Yeah.
the extension of the wire. What else? Did we cover all? We, F is done, L is done, A diameter is done, extension is also done. So these are the quantities that you need to measure. Okay. Then what's the part D? Sage which is the independent and what is the dependent variable. The independent variable is the one that you can change. Okay, that you can change. So which variable can you change directly? Can we change the weight by just replacing this by another weight? Can we change the weight?
Yeah, we can.
And what's the other independent variable that we have in here? Can we change the original length of the wire as well?
No.
Why
I mean,
not?
we can change it, but
We can
no,
change
we
it,
can
right?
change
So yeah, both of them are actually the independent variables, but weight is a better answer, okay? Weight is a better answer. Weight, or option D is weight, or the load itself, or whatever. It's up to you, weight or load. Then it comes, and the dependent variable is extension, okay? If weight is the independent variable, then the dependent variable is the extension. Then the extension is the dependent variable. Then option D, then comes E. For one of the quantities listed in C, explain the choice of measuring the instrument. Measuring instrument for one of these quantities. So we measure diameter. For the diameter, let's use the vernier caliper. Okay, diameter can be measured using the vernier caliper. Since the diameter of the wire is very small and cannot be measured using a normal meter rule, of course, right? It's very small. That's the explanation. Then after E comes F. Comment on whether repeated readings are appropriate. Repeated readings of the measurements that you did in part E. Well, repeated readings over here of option D. Well, you don't need the repeated readings. All you need to do is just measure it once. But for the quantities that you do actually need the repeated readings are the forces and the extensions, right? A force and extension, because you'll need to draw out a graph of them. Independent variable needs to be repeated. Does not need to be repeated. This D, no need for the repetition. But if you do repeat it, there's no harm, but there is no need actually. Let's see what they wrote over here. Justification, measure the length, comment on whether repeated, comment repeats of values are appropriate, but the load must be such that the wire stays within the elastic limit, are appropriate in this case or not. This is just a comment. So this is, they've given you one example. You can say that repeats are needed, or you can say the repeats are not needed. Okay, over here they use the extension. So yes, of course, in extension you do need to repeat it because that's a dependent variable, and you'll need to draw out the graph as well. But and that's also inaccurately measured, right? The extension, you can't measure it very accurately using this setup. So you'll need to measure it again and again. But for the diameter, you are using the the vernier caliper, so no need to repeat it. No need to repeat since the vernier caliper is a very accurate device.
it. Okay.
Yeah, so you can measure it since vernier caliper is very accurate. Or you could just, instead of this, you could use the extension as the quantity, or you could use the force as the quantity. And for those cases, you'll need to repeat them because you need them for the graph making, right? For the plotting. And then the next one says, explain how the data collected will be used, including a sketch of the expected graph. How the data collected would be used. Okay, what sketch would you use? EF, then comes G. So for different values of the force, different, or the extensions, the corresponding extensions are measured. Corresponding extensions are measured, and a graph of force against extension is drawn. So they also want us to draw a sketch of that graph. So you just draw a graph like this. Okay, this is a force extension graph, right? You know that E is equals to FL over AX or AE, right? X is the
Yeah.
extension. So
Yeah.
you rearrange it,
Wait,
so
so
it's gonna
your voice.
become, you rearrange it, so it's gonna become EA upon L times EX, right? So EA upon L is constant, so F is proportional to X, and the graph of direct proportionality is a straight line passing through the origin, right?
Yeah.
If force is proportional to extension, it's going to be a straight line passing through the origin, given that it stays within the limit of proportionality, okay? And we are drawing a graph of within limit of proportionality, so we don't need to worry. And then after that, explain how the data is collected will be used. So you take different measurements of the force and then the corresponding values of extensions. Explain the main source of uncertainty or the systemic error over here in this experiment. It's for 2 marks. Okay, and this sketch and the explanation has 4 marks actually. So I think you'll also, it's better to give an example that force in newtons. Okay, and by the way, for the sketch you need to mention the units as well. Okay, force is measured in newtons and the extension is measured in meters. Okay, so
Okay.
then after the graph, you will need to calculate. Okay, it's better to even tell them how you can calculate the Young modulus, to tell them that the gradient of this graph, is equal to EA upon L according to this formula. Okay, this is the gradient. And so the Young modulus can be calculated. You have to write it down in words, okay? By using the formula gradient into length divided by area. And then once the Young modulus has been calculated, that's the answer. The main source of uncertainty. Well, the main source of uncertainty over here could be this length extension measurement, because we are not sure if this is gonna, where will it get extended. It's difficult to extend because the extension is not very appreciable or not very large enough. Secondly, we don't know if the wire has exceeded its limit of proportionality or not. Okay, and what else could be the source of error over here? Extension area. Okay, area might be measured inaccurately using the diameter might not be accurately measured using the Werner caliper. But they want us the main source of systemic error could be a zero error over here. Zero error, right? Why a zero error? Because this pointer, what if this pointer is slightly in front of the zero mark? Then the point where it will go will not be the point of extension. Or there could be, okay, the pulley, this pulley over here, it might not be lubricated. It might have friction. So the friction in the pulley might not give an accurate value for the force over here, right? This is one possibility. meaning the force means the weight, okay?
Okay.
Yeah. But let's look at the marking scheme for these additional points. And then we also need the safety. So for the safety, well, this is quite safe experiment, okay? Unless the string breaks and it falls down on your leg, it's safe, okay? Apart from that. So, well, safety, if you want to comment on it, it's quite a safe
Also,
experiment.
we could wear goggles, safety goggles, in case the wire snaps.
Safety goggles, yeah, to protect your eyes. Okay. Yes, you can do that. In case the wire snaps, yes, it will. Or the apart from that, if the weight falls down on your leg, so prevent keeping your leg beneath the weight, or prevent touching the pulley, otherwise your fingers might come in it, and stuff like that. Okay, any reasonable comment would be accepted over here. But let's see what they actually want us. Let's read the marking scheme now. Draw and label a diagram for the experiment. Drawing should have an appropriate arrangement with means of securing the wire, mass, and hanger, वगैरह वगैरह. Okay, we did that. Then list an additional apparatus required that is not shown in your diagram. Micrometer means measuring extension if not on the diagram. Okay, means of measuring extension is actually the scale. We did show that on the diagram, right? This one, this scale over here, this one. Wait, this one. Then state the quantity. So the diameter, original length. See, original length. They didn't say length. They said original length. That's a key term. Okay, original. Then extension and the mass or force. Then state which is an independent variable and dependent variable. So identities could be the mass or the extension or the final length as the variables. Correctly identifies the independent and dependent variables. So I did tell you how to identify them correctly. The one which you can change is the independent variable. The one that gets changed as a result of changing the independent variable is the dependent variable. Then for one of the quantities listed in C, explain your choice of measuring the instruments. So quantity and instrument justification. Measure the length with the meter rule as the readings are to 1 millimeter, which is small compared to the expected length. Okay, so readings are measure length with a meter rule as readings are to 1 millimeter, which is small as compared to the expected length. I hope you got this point. They're using the meter rule because their extension could be within 1 millimeter. Okay, so this 1 millimeter, within 1 millimeter, sorry, not within, they are to 1 millimeter, or meaning the readings are 1 millimeter or more, right, for the extension. So they can easily be measured using a meter rule, but all actually not easily, but like it is measurable using the meter rule. Or there could have been better ways as well, but we also use the same technique over here. We placed a meter rule, so yeah. But this is just one example. Any suitable answer is accepted. For instance, we wrote for one quantity, we wrote vernier caliper for measuring the diameter. Because the diameter is very small, it is less than 1 millimeter, so we can use the vernier caliper. It would be better to add the 0.1 millimeter over here. It is less than 1 millimeter because you know that vernier calipers, they measure up to 0.001 centimeters, right? So
Yeah.
less than 1 centimeter readings could be measured using that. Then after this comment on repeating the reading, so it again the comment has to be appropriate if needed and if not needed. Okay, if extension is measured, then obviously you'll need to repeat it again and again because extension is not measured that accurately in one reading. And then explain how the data will be used to sketch a graph. So we've used this use of pi d squared upon 4 to calculate the area, use stress strain and then stuff like that, and the Young modulus is a gradient. Or you could use this to mg, or yeah, this one, the second one has been, we did the second one, use of pi d squared to calculate the area. Okay, we did mention this. We did mention f is equal to mg. We know that, right? We know that, but we didn't
Yeah.
mention that. We didn't mention it, so it's better to mention that as well. Force extension graph, we did say that we need to draw out the force extension graph, and this is how you calculate the Young modulus. We did mention that as well. That Young modulus can be calculated using E upon L and gradient into L upon A. Gradient into L or X upon A. X is the extension. Okay. Basically, our method is correct. Okay. These are just two examples. Just two
Okay.
examples. Okay. How to do that. See how data, explain how the data would be calculated. Then explain the main source of uncertainty. Extension or diameter is very small, so large percentage error. Okay, that could be an answer. And use goggles to prevent the injury if wire breaks. So exactly your point. Remember? If the wire
Yeah.
snaps. Yeah, good work. You got the safety mark. This goes to you. And explain the main source of uncertainty. So it's going to be actually the extension and the diameter, both are very small. Yeah, that's a very valid point. They are actually small. The diameter is going to be in less than 1 millimeter or less than 1 centimeter. So that's why we use the vernier caliper. And this extension is also not going to be significant. It's also going to be very small. So yeah, due to that, the percentage error is going to be very high. Since you know the formula for percentage error has the value in the denominator. If the denominator becomes small, error becomes large, okay? And then goggles. See, we are done with this question, and this easy,
Yeah.
not that tough, right? As you know, basically for such, now I get it, for such questions, this paper is actually similar to paper 5 of Cambridge A levels, Cambridge A2. Okay, this is similar to A2. In A2 you get a 15-mark question just like the one, just like this one, and in that you need to design an experiment, you need to show how to draw a graph, okay, just like this one, and you need to show that what will the gradient represent, and then you'll need to finally comment on the safety measures as well for 1 mark as well. So this is quite similar to that one. So well, for that paper, what I advise the students is to do as many past papers as possible, because these, for these papers you'll actually need the theory, the basic theory, and in addition to that some past paper knowledge as well, because the marking scheme, the key terms which are used in the marking scheme, these are very important. And once you do like 5 to 10 papers in a row, you'll get a hang of it. You'll know that what the examiner actually is asking. Okay, this was actually a question directly from the theory. That's why it was pretty easy. But later on, even if you get an experiment that you've never done in your theory, the steps are going to be the same. The steps are going to be the same. You'll just need to use your common sense and see which one is the independent and which one is the dependent variable. You'll need to see which apparatus needs to be used. You'll need to see which quantities needs to be measured. So it's pretty easy actually. It's not that difficult, but the thing is, it will become difficult if you do not have enough past paper practice for it. So I would suggest
Right.
do as many past papers as possible for this, because the marking scheme will give you all these points. Most of these points, these, the zero error and stuff, I learned these from the marking scheme of P5 actually. Okay, so you can learn it from the marking scheme of your P3. So now the next question. Okay, this is a practical question. Okay, this is similar to our paper 3 in physics, practical. Okay, so criticize these results. You'll need to criticize them and then complete the last row and then explain why the graph of R on the y-axis against L on the x-axis should be a straight line through the origin, or we'll need to explain that. And then we'll need to plot the graph. It's simple. You know what? In paper 3, this question format is exactly identical to this one, but the difference is that these values are not given. Then what to do? Well, if they are not given, the apparatus is given to you in the lab, and you have to measure out the values at different values, and then you have to record them over here. Get it? Over here, the examiner has actually made it easier for you. They've given you the recordings themselves.
Okay.
Yeah, so now you have the current, length, voltage, and resistance needs to be calculated for a wire. What's the formula for resistance? It's rho L over A. But where will you get the rho from? Okay, you can't get the rho. Then what's the other formula for resistance? Well, you can use the formula V is equals to IR. So the resistance is equals to V upon I. So voltage divided by current will give you the resistance. If you look at these values, these have also been calculated using the same methodology. 2 divided by 6.8, it is 0.294, right? 2 divided by 4.5, 0.44. 2 divided by 3.4 is 0.59. And over here, you can give your answer to 3 significant figure. It's always going to be correct. Okay. either 2 or 3 significant figures, but the 3 significant figures will always match over here, because the significant figures, they must match your independent variables significant figures. Independent variable is actually the length, and in this case it's actually the current that we are using, right? The voltage upon current. So voltage and current, these two quantities, these significant figures must match these two quantities. Okay, in this case here we have 3 significant figures, so these are 3 significant figures, 3 significant figures, but these are given to 2 because these are 2 significant figures. Okay, so you could give your answer to 2 or 3 significant figures. Now coming to this one is 2 divided by 2.3. So what's the answer? It's 0.8695 actually. So we can round it off to 0.870. But I'm not going to write it as 0.870, but rather I'm going to write it as 0.87. Okay, 2 significant figures. But you could give it to 0.870. It's correct. Okay, either 2 or 3 significant figures. Now we need to criticize these results, that all of them need to be in 2 significant figures. So the mean or average is not taken, repetitions are not shown, repetitions are lacking, no mean values shown, no mean values, no average, incorrect significant figures or decimal places. Complete the last row, we did that. Then they're saying explain why the graph of R on the y-axis against on the x-axis should be a straight line through the origin. So what's the formula of R, which is rho L upon A, right? Rho and A are constant. So what's the relationship? R is proportional to the length. And if it is proportional, then for proportionality, it has to be a straight line passing through the origin. Okay. That's why it's going to be a straight line passing through the origin. Get it? You have to mention this formula, then you have to say that this factor is constant, therefore it's going to be a straight line. What does the marking scheme say? Comparison is this with this formula. Yeah, y is equal to mx plus c. We did that. Y is equal to mx plus c. This is a straight line formula. Remember in your O-level math, and c is 0. Since in this case the c is 0, this is the y-intercept. So y equals mx is the only thing which is left. So therefore it's going to be a straight line passing through the origin because the intercept is 0. Okay. And rho upon A is constant. I have to mention that as well. Constant means straight line. See, intercept being 0 means passing to the origin. This is the intercept. If it had an intercept, meaning for example plus 5, then this graph would have been passing through plus 5. And if this wasn't constant, then it would have been a curve. Clear?
Yeah.
Okay. Plot a graph on the grid provided and draw a line of best fit. For the line of best fit, you will get plots which will be scattered, okay, which won't be lying perfectly on the graph, but you have to actually draw out a line that is in which the graph or the plots are quite close to the line, okay, or they are as close as possible. So, and you have to choose an appropriate scale as well. This is the y and this is the x-axis, and it keeps on going up and down. Okay, on the x-axis it's always the independent variable. Okay, the independent variable in this case is going to be the they want us a graph of R against L. Okay, they told us the dependent and independent. The independent is the length. So on the x-axis you have to label the length and its unit as well. The unit carries marks. Okay, the unit is meters, so it's going to be meters. Length in meters. And on the y-axis you'll need the resistance and its unit, which is ohms. So you have to label the y-axis with resistance in its units, ohm. Okay, now once you have the resistance and length with the units labeled on this graph, then you'll need to choose an appropriate scale in order to accommodate all of these values in there. Okay, but you need to change these 3 significant figures to 2 significant figures. This is going to be 0.29, this is going to be 0.44. Okay, and this is going to be 0.59, this is 0.74, and this is 0.87. And now just draw out the graph. So it's from 1 to 3, and this is from 0.29 to 0.87. And listen, your scale should be such that it should be covering more than 70% of the graph. Okay, if the graph is being covered less than 70%, then less than 50% of the graph is covered, then you might not get full marks. Okay, so you need to use a graph a scale that would cover the maximum possible area of the graph. So if you look at the length, is it starting from the 0 point, or is it not starting from 0? First of all, let's look at the length values. Okay, just a second. Length is starting out from 1, so you have to start out from 1 and go all the way to 3. So let's start out from 1. The origin is not taken to be 0 in this case. Okay, it's taken to be 1, and we have to go all the way to 3. So let's say this is 1.5, this is 2.0. Okay, this is not 1. Okay, it's 1.0. Okay, keep it to 2. 2.5 and then 3.0. Still small? Well, it will cover at least okay, how 1, 2, 3, 4. It's small. Sorry, this won't cover more than 50%. So we'll need to use a larger scale. Okay, so I know what to use. And instead of taking 1, this is 1.0. Okay, this is 1.0. Then this is gonna be 1.5. Why did I take 3 significant figures? Okay, and then this is gonna be 2.0, 0.5, then 3.0. Okay, exact. We covered the entire graph. Clear? Is this scale clear?
Yeah.
Okay, starting from 1 going all the way to 3. So the y-axis has been sorry, the x-axis has been covered. Now what about the y-axis? It's starting from 0.29 going to 0.87. Consider this as 29 and 87. Okay, so starting from 0.29. Okay, so let's start out from, let's say, where should I start it out from? Let's start out from 0.20. Okay, 0.20, 0.3, and 0.4. Go up 0.5. Okay, keep them to 2 significant figures. Okay, 0.60, 70, 80, 90. Okay, how much of the graph is covered? 1, 2, 3, 4, 5, 6, 7. 7 boxes. And what are the total number of boxes? 8, 9, 10, 11, 12. Well, we actually did cover more than 50% of the y-axis. So I think this should be fine. But still, if you could make the graph even better, the y-axis graph, so try doubling it up, then it will reach up there.
Sir, your voice.
I said that this graph is still more than 50%, but in order to make the graph even better, try doubling these values. So 0.2, then this is gonna, let's make this 0.30, this point. Then this point at 0.40. Then 0.60. Zero 0.80. Then finally 0.90. Yeah, now this graph is better. You use the scale given off the graphs. Now all you need to do is just plot them in. So will you be able to do the plotting?
Yeah.
Hopefully. Hopefully this won't be that easy, but still you'll be able to do them. So at 1.0 it's 0.29, right? So at 1.0 x-axis is gonna go all the way to 0.29. So this is 0.2, 0.21, 22, 23, 4, 5, 6, 7, 8, 9. Where is 9? Is it over here? Yeah, this is 0.29. So this is your first plot. The plot must be a cross, okay? And it must not be very big. It has to be small. And then keep on doing this again and again for the rest of them. Clear? I hope you can draw out a graph over here. And then you need to use it to determine the resistivity of the material. So what do you think is the resistivity of the material? R is rho L over A, right? Rho upon A represents the gradient of the graph. So you can use the graph to calculate the gradient first. Okay, to calculate the gradient, again, I'm telling you, if this is your graph, if this is how your graph is made, then you must take 2 points which have to be very far apart from one another. And after taking those 2 points, you have to draw out a triangle over here from those 2 points, okay? Do you know how to draw this triangle? The rise over run triangle?
Yeah.
Okay, you have to show the triangle in case of practical. And this triangle's hypotenuse should be large enough to cover most of the graph, and then use those 2 points to calculate the slope or the gradient. Once you have the gradient, you plug it in here, and then what you do is to calculate this raw, you multiply the gradient by the area, but for that you'll need to use the diameter to calculate the area first using the formula pi d squared upon 4, but for the d you'll need to convert the millimeters to meters as well. Clear? So 3-4 steps, and then you'll get your resistivity. And then last one, suggest 2 techniques which would ensure that the results are accurate, obtained are accurate actually. Okay, any 2 techniques in which, okay, over here you cannot say that repeat the experiment and take the mean. Why? Because we already have the graph drawn, right? The graph does have the repeated values on the x-axis and on the y-axis. So we need some other technique over here. What other technique could we use over here? Remember the repetition of the current and the voltage, we could use that. And what else can we use? We could use a larger range of values of length than 1 and 3 meters. The range of values is very narrow, right? It's just 1 to 3 meters. We could use a more broader range over here to get a more accurate answer. Let's check out the marking scheme for this one. Best line of fit, and then triangle may be determined to determine the gradient. See, use of large triangle, that triangle which I told you. Area calculated and resistivity, example of calculation, and then switch off between 2 readings to prevent overheating. Repeat the diameter readings at different positions or orientations. Check the named instrument for 0 error. Okay, these are the 3 points which they have given. You could use them. Okay, let me explain them. Switch off between 2 readings to prevent overheating means that when you are measuring out the when you have already measured one reading using the voltmeter and the ammeter and the stuff, then you should switch it off to prevent overheating. Then the second part says that repeated diameter readings at different orientations of wire. What's the benefit of that? Well, the benefit of that is you actually get a range of values. Okay, over here it's a different value, over here it's different, over here it's different, and then you could just take an average of those diameters, right? And then name the instrument for 0 error. Which instrument can we check for 0 error? In this case, we can check the ammeter or the voltmeter or that meter rule as well. Okay, all of these instruments can be used to check for the 0 error as well. Is that clear?